A. I don't know. Oh, yeah, that one, they clearly indicated what they meant there. A. This one's got math on it, with no decision. A. 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 You can circle on that one, it's hard to find out. A. B. Oops. B. That must be A. A. Unless you're about waste, you should get the 99 cents because you get more for your money, but then you also have to change the light bulb more, and that kind of stinks. But I guess that person was going to get A. 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 B. A. So I got 1, 2, 3, 4, 5. 5 of you. Was there like 25 people in the room? So, I don't know, somebody count. How many people are in the room? No. So I get the B's. I know who's going to pay $6.99. 5 of you will pay $6.99. Stand up if you pay $69.99. Now, I will grant I did not tell you the light is $69.99 gold. But I don't care what the light is $69.99 gold. I mean, you could assume that it's equivalent or better than option B. You stood up. Why'd you sit back down?
Oh, you want to say
I figured I'd give other people a chance to stand up and join you. The rest of you guys look around. Because you're going to work for these guys someday.
Yeah.
You guys think like managers, not like light bulb purchasers. So there's a backstory to my light bulb question here. I used to, in a previous life, I owned and managed many rental properties. It's actually what financed my frivolous lifestyle. And when I started that business, I would go to the discount store and I would buy the cheapest damn light bulbs they sold. And I spent a lot of time walking through the discount stores back then. And every time I'd walk through the discount store, if they were having a sale on light bulbs, I would stock up. And I would buy 10 cents a piece light bulbs, right? And then the longer I did that business, granted we had more properties, I was also doing other things. I was working as an engineering consultant. When I was doing my engineering consulting, I could bill myself at $2,000 a day. And so I could be at the apartment changing light bulbs or trying to sell that $2,000 a day consulting time. And so I started thinking about it, and I stopped buying cheap light bulbs. And granted, I didn't buy the most expensive light bulbs I found. I bought the ones with the longest published life that I could find. And think about the cost of changing a light bulb for somebody in that position. When does the phone ring? No. But it rings when you're in the middle of Sunday dinner with your friends that you invited over. Maybe they flew in from somewhere else. And is the tenant happy or unhappy when it rings? Unhappy. You know why? Because it hasn't been working for a month. But they didn't tell you, and you never go there when it's dark, so you didn't know. But they're unhappy. And so then what do? You go over and you look at it. So you got here's the light bulb. Then you go back to the barn, and you get the ladder because you can't reach the light bulb. And then you hunt all over for where you kept those cheap light bulbs that you stocked up on when you went to the discount store. But it hadn't really become adept at lean manufacturing systems at the time of being this instance. And so you can't find it. So then you drive to Home Depot and you go buy a new light bulb. Then you drive back there and you stand the ladder up on the staircase to reach the light bulb that you can't reach. And now you've changed the light bulb and you get back and your friends have all gone home. So the cost, not even thinking about the opportunity cost, could you have sold that time doing consulting work or something else more valuable? So I would buy the $69.99 light bulb.
I only buy it at 700,000.
So I mean, there's a number. If it was 40,000, so I had your 20,000, I had 40,000. If it was double, fine, even though it cost more than double, because the opportunity cost is the thing I could have been doing at that time. Not everybody's in that situation. You may want to buy the 99 light bulb yourself. But let's talk about manufacturing and cost. So we said that here we were going to introduce you to manufacturing science and engineering, CNC controlled machining, manufacturing, CNC machining, science of manufacturing, machining with performance, manufacturing process science and engineering. Oh, in school, the class, right? Students whose project work will necessitate fabrication of parts. Everybody qualified there? Everybody has a realization degree when it's an engineering degree, right? Everybody has to make something. Okay, all right. So, what did we talk about on the first day of class? Anybody remember? We did talk about what we wanted to get out of the class. What did I want to get out of the class? Did you remember?
We wanted to get our money's worth.
I wanted you guys to feel like you got your money's worth. It's all about feelings, especially in today's day and politically correct age. It's all about feelings. So I wanted you guys to feel like you got your money's worth. I wanted you to actually get your money's worth also. What else did I want to get out of the class? So what's sort of my objective in the class? So you may remember that I want to make engineers that understand something about manufacturing so that later they could design things that can be manufactured. That's sort of my tagline, making engineers that understand manufacturing. So I want that. So we spent, like 2 days talking about money at the beginning of the class, right? So why are we talking about money again? Well, one, because they say to make every presentation in football. Tell them to tell it to them. Tell them to spell them. You never read that before? Oh yeah, every paper, every presentation, they like the class as a whole is like a presentation, right? One long presentation. Long, right? But so I can talk about money at the beginning of the class. Besides the fact that it's more fun to have something than it is to not. What was our objective at the beginning of the class when we started talking about value and new manufacturing, profit rate? What was our objective? Final exam. Right. We're all eventually going to have a job somewhere. Most of the companies we're going to work for are going to make something. And we'd like to make our company profitable so that we can keep that job and maybe move up to another job. So we'd like to, so one, it's good for us personally. So that's how you actually receive value, is if this helps you in working for a company, retaining a job, making a job. It's good for the society as a whole, because we actually need new things to be created. We're not growing, we're dying. So we need that. All right, so we talked about it there at the beginning. So today, so when should we change tools in our machining operations? So we would like to change them as infrequently as possible because I didn't hear that enough. Well, so there's time. So why is time a factor? Why do we care how much time? Yeah, we do. The typical rate for the type of machines that you guys would use in a lab is about $100, $150 an hour per machine plus operator. So it costs $150 an hour whether that machine is sitting on the floor, not making parts, or producing parts. So $150 an hour is a good reason to want to save time, and it takes time to change that tool. And if we're changing the tool then we're not making parts, presumably, right? Okay. So we would like to change our tools as infrequently as possible. How frequently would we like to change our tools? When do we need to change the tool? Yes. When it's no longer useful. So when it is stopped, well, actually, do we want to wait till it's no longer useful?
You want to wait until it starts to stop. Because you can get a tool installed, it takes forever.
Right. So what happens as the tool becomes dull? So when we're doing our cutting, right, if we're just looking at a cutting operation here, there's my tool, there's my sharp cutting point on the end of the tool, right? My workpiece is here, my chip is flowing up that way, right? And so the workpiece is moving that way past the tool. You guys are all tired of this drawing by now, right? If you go into manufacturing engineering, you're going to see this drawing a lot. Manufacturing engineering professors like to draw this drawing. It makes us feel like we're artists and mathematicians and whatnot. Right, so what happens as the tool becomes dull? It takes more energy. Why does it take more energy? Well, so when we get the sharp, so we've got our shear plane aligned like this, right? Well, we've got the dull tool. Our shear plane is going to end up like that because our uncut chip thickness is still the same, right? We haven't changed our feed rate or our side edge cutting angle. That shear plane is a lot bigger, right? Our shear stress depends on this length and the width of the chip, right? So we've got our length of our shear plane and the width of our chip. And so if our shear stress goes up, that means the force has to go up, right? If the force goes up and we haven't changed the velocity, then the power goes up. Power goes up, so one thing that happens is it takes more energy to make the cut. Our light bill goes up. The second largest concern of manufacturing companies in Massachusetts right now is the cost of electricity. The largest concern is the fact that they can't hire anybody that can run their machines because there are not enough people with training. Second largest concern is the cost of electricity. I mean, heroin's in there too. But that's one of the reasons that they can't hire people. There's a big drug problem in Massachusetts right now. Did you guys know that? So you learned something today. If you didn't know that, there's a big heroin problem in Massachusetts right now. It's cheaper to buy heroin than it is to buy the prescription painkillers for when you get injured. So people can't afford to buy their Vicodin that the doctor prescribed when they broke their hand, they get hooked on heroin instead. This is a man that knows his pricing. Just get a profit rate figured out. All right. So as the tool gets dull, it takes more energy to make the cut. So there's a problem. What else happens as the tool gets dull? Yeah. Yeah, that shit happens as the tool gets dull, right? So you change the surface texture of the finished part. So that's a problem. What else happens? Oh, so what happens? So my force went way up, right? Like we usually draw this with force on the chip, but there's equal and opposite force on the tool, right? What happens when the force goes way up? Tool breaks. When would we like to change the tool? Before it explodes. Presumably before we get detrimental effects, right? So we would like to change the tool as infrequently as possible, but as often as we need to so it doesn't explode. Right? Okay, perfect. what fact, based on your understanding of physics and machine processes, what factors influence the life of the tool?
I know, I can tell you the answer.
Okay, so well, the life of the tool will, so how much pause it gets in between uses, you mean?
I was saying more along the lines of,
So how are we going to define a metric for tool life, right? We can't measure it, we can't control it. So how about we just call it number of hours engaged in cutting. Right, because that's like our light bulb life. The life of our light bulb is how long have we had the light turned on, right? That's what they report there. So what is going to, so I think that's not a factor in the number of hours, right? That's just another way to count the number of hours. Yeah. Right, so the things we get to control are feeds and speeds. And so, believe it or not, people have thought about this before. And so, this guy named Taylor came up with an equation that could predict how long a tool would last in production. How did he do this? This can answer faster, because I only get 20 minutes, otherwise Travis is going to break my arm. But not lose that finger. So, how did Taylor come up with this equation? Or come up with this graph? There's an equation also. We haven't seen the equation yet. How did Taylor do this? Yes? Yeah, he did some experiments, right? So this is experimentally generated data. And so it turns out that the log of the cutting speed plotted against the log of the time it took until the tool was no longer useful always makes a straight line. Scientists like it when stuff makes straight lines, because that means you know something about it, right? You can make an equation. And so the thing that happens here is the tool life, T, here, equals some constant C divided by B to the 1 over n power. Or, sorry, the value C here. Okay, so now we can predict tool life if we've done some test cuts with the tool. What does our prediction of tool life allow us to do? Oh, so it's dependent on speed, right? Velocity. What does velocity also impact? It impacts, go ahead, Nick. Presumably cutting force is equivalent here. Let's go to our material removal rate equation. We move the tool faster to the workpiece, then we remove more material more faster, right? We fill the buckets with chips more quickly. We can ship more products to our customers more quickly. What does that do for us? It lets us drive our profit rate, right? We'd like our profit rate to be as high as possible. Now, what's the presupposed assumption that we have here? When we're driving profit rate by making time go down. What's it take to make a profit? Right.
well, it's an assumption that it's not costing anymore.
So we're going to find out that the cost is impacted by the tool life and the velocity also. So it's going to be time here and here, value is going to stay constant. So as we solve this equation, we're going to see that. But what is presupposed if we say if I make the parts faster, I make more money? It's presupposed that there's a customer waiting for that part, right? Don't speed up the process if nobody wants to buy the parts. Okay, so keep that in mind whenever you're doing this kind of analysis. But we got our tailored tool leg. So here's some examples. And so these are all slides that are in the link for the presentation. You can see all these. But here's some examples of some of this data for different tool configurations in different types of steel. And so this is some examples from experiments like this. If we do that, now, so we know that if we speed up the process, we can make parts faster, we can sell parts faster, we can increase our profit rate as long as our cost doesn't go up too much, right? What's in the cost? So we said we want to change tools as infrequently as possible so that we can save time of not making production, right? So part of that cost is going to be the time it takes to change the tool. If you can change the tool with no time, then buy the cheaper tool, right? It takes 0 time to change the tool. How do you make it take 0 time to change the tool? Well, not just automated though, because if we stop making chips while the automated process is working, we've eliminated the cost of the person doing the changing, and we've amortized that over the cost of the robot or whatever that's doing the changing. Yep. What if I have 2 different tools? And so now I can make the time to change tools be 0 by simply having the program adapt, and as the pre-selected time, this tool is supposed to be worn out, we simply change the tool number in the program automatically without pausing production. And so you never had to stop the machine to change the tool. And so there's actually, I've seen machine tools with, so we've got the rotating turret tool changers on the mini mills. You guys saw the when you did the first lab, you used the VM2. So the mini mills have 10 tools. The VM2 has 25 tools on the carousel. I've seen machine tools just like that VM2, but in a production setting where they had a chain drive that was feeding tools to that turret, and you have 1,000 tools in the chain drive. And part of the reason is so that you never have to take the machine out of service to change that tool, because I can now there's some other automated things you have to be able to do. You have to be able to set the tool length without taking the machine out of service, right? So you can't use our probing macros that we're using, right? There's other ways that you can set those tool lengths. So you make that tool change time go to 0, but in a normal operation, you stop the machining process, the operator takes the old tool out, puts the new tool in, sets the tool length. There's some finite time that has to happen. It reduces our ability to, and it has cost because you have the operator time. Okay. What do you think makes the tools wear out? Anybody chemistry major? Chemical processes impact this. What causes tools to wear? So some corrosion, although not like I left it out on the deck in the rain and it got rusty. I mean, that happens too. So corrosive chemical processes, things like that, they happen faster with heat. What do you think the temperatures are at the tool chip interface? They can be up to thousands of degrees, but yeah, lots of degrees. Heat change that. Anybody know the Swedish physicist, chemist named Arrhenius? No, you're not going to get my idea. Arrhenius got the Nobel Prize for pointing out that chemical reactions increase speed with temperature. And in fact, they do so along the same curve that we defined with our Taylor equation here. So the log of the temperature is the log of the Gotcha. What goes into the cost of cutting the part? What I'd like to do is make the cost of cutting the part be low. We know that what we're trying to do is optimize for the speed at which we run the spindle. We know that so tool life goes down logarithmically as we increase speed. And Taylor has seen that here. What goes into cost per cut? You're the manufacturing engineer. Your job is to figure out how much is it going to cost to make this widget. I just did this yesterday. I had a drawing. I had to estimate the cost of making it. We're going to make 30, 300, or 500. Yep. Nick. So more broad. Yeah. So time it takes to set up the machine. Non-productive time, right? So we're not producing value for our customers. What else? Because of the cost of making a part. So the more parts you're going to make. So I did a quote yesterday for a part for a company I work with, and they said, here's our parts. It's an assembly with 3 components: 2 stainless steel, 1 Delrin. And they said, we're currently testing the prototypes that you guys made us. We want to quote now for 30 parts so we can expand our tests. If our test works, we want a production run of either 300 a year or 500 a year. What's going to be the costs, right? And so that setup time has a higher impact on 30 parts than it does on 500 parts, right? Because I amortize that setup time across all the pieces we make. What else? Yeah. So the cost of raw material. I can make the cost of making the part go down by wasting less material, right? So the impact of the cost of the part is the cost of the raw material. Yep. The cost of the tooling, the cost to buy the tool. Yep. Cost of the worker. The cost of labor, the person that's operating the machine. I can make that cost go down by having you operate 3 machines at the same time, right? Because you have your little feet. You have locomotion. You can move from this machine to this machine to this machine back to this machine. If we timed all those operations correctly, you spend time, and the time it takes you to walk to do the work in this machine and walk to the next machine is the right amount of time for that next machine to be finished. Because that next machine needs more time when you put it further away, right? What else goes into it? We said cost of raw materials, cost of the tooling, the cost of the operator, cost of the setup, and so the cost of when the tool is actually engaging the material and making value. So there's cost of cutting, cost of changing tools, cost of the tool itself, cost of the raw material, and all of the non-productive costs that go with that, like the cost of writing the NC code, right? The manufacturing engineer, non-value added. You can't do the job without him, so it's waste that we can't get rid of. What do we call that? Lean? Waste that you can't eliminate? Anybody remember the word? MUDA. M-U-D-A. Those are wastes that you have to have and can't get rid of them. Cost of cutting, cost of changing tools. All right, which ones of these have a velocity impact, right? What we want to do is have the optimal velocity. I'm watching my watch on my arm break. Non-productive costs. So these non-productive costs are not impacted by the speed at which the tool is moving through the workpiece, right? What goes into non-productive costs besides you guys? You guys are non-productive. What goes into non-productive costs besides engineering and machine setup? Yeah, keep the lights on. Lights out manufacturing, less costs. You guys seen those new robots that they have that like you can interact with people and they can't hurt people if they bump into you and stuff like that? You guys seen that? Anybody? Somebody nod their head? Really? There's a bunch of them. There's like this, the Baxter. There's one of those on campus. There's one called Sawyer. It's like a Baxter, but it has more arms. Too. I think it has 2 arms, I think. So one of those Sawyer robots cost $38,000 to install. How much do you think it costs for a sheet tool operator to install? About $60,000 to $70,000 a year with all the taxes and things, insurance benefits. So at least for a basic, this is like Joe off the street. You taught him how to press the button. This is not a fancy machine setup operator. $60,000 to $70,000 a year. You might see a lot of Baxters. You might see a lot of Sawyers in those positions. But none of that impacts the velocity. Doesn't impact any of that. Now, cost of cutting. Right? This is when the tool is engaged making a chip that the customer wants. Velocity is important here, right? Presuming somebody wants to buy all those things. Right, so you can go through these. You can look at each of these items in and of itself, and you can say which ones have velocity or have a time impact, which ones don't. You get rid of the ones that don't. And you can solve this equation and find T, so that's tool life as a function of V, for a given C for your tool. Then you can solve the equations, or you just make the graph. You're collecting the data, you just make the graph, right? And so you find that if you add cost of cutting together with the cost of tools and tool change, you can find where those two cross. There's a minimum, and that is your optimum speed for moving the tool through the workpiece. You remember when we did our cookbook process variable selection, when we look it up in the catalog, it gives us a range of cutting speeds, right? I mean, those Kennametal tools that we use in lab are like 0 to 6,000 surface feet per minute, right? Which means that they should presumably not break anywhere in that range. And so you take one of those tools, you can do your experiment, or you could figure it out from math and do this. Like 30 seconds left. This is the last slide. That is amazing. The pizza should be here any minute. I do know a faculty member who has had pizza delivered to his class just as he was handing out the post evaluation. And I've always wanted to try it, but I never remembered to order pizza. I did try it once. I sent a work study over to Jake and ordered pizza just before I went to class, and they're like, there's no way we can make that much pizza that fast. I should have planned ahead. I have had a lot of fun with this class. I hope you guys have. I've had a lot of fun with this class. I hope you guys have had fun, but also learned something. So if you're in, anybody have a pen? Here, I got the chalk. Section 1, this is section 4. So section 4 has lab Tuesday, Thursday from 3 to 5. So please put your evaluation form back in the correct envelope at the end, because the registrar gets really pissed off when I send them all back in one envelope, and then they think I didn't give them to the other sections. Section is Tuesday and Thursday from 1 to 3. Section 2 is Tuesday and Thursday from 9 to 11. Monday and Wednesday, and I'm not going to bother right the time because there's only one lab on Monday and Wednesday. So they think that I'm going to. They used to give us those fancy resealable ones, the little metal clips. I guess they're cutting costs. So they instruct me that I'm supposed to leave the room when you guys release out, so it doesn't bias my grading of you. Oh, extra credit thing. I'm going to complete the final grades for the class before I grade the extra credit assignments that you handed in. Because if you already have an A, I'm not going to bother to grade yours. That saves me time. I know there was some people that wanted to know whether or not they needed to complete the final exam, and they wanted to get their extra credit back sooner. But I'm gonna err on the side of saving me time, not saving you time. And I promise that if you start filling this out before I leave the room, I guess you didn't need the whole stack. That's not right. I promise if you start filling it out before I leave the room, I won't look at your answers and I won't know that it was you anyway. And they can save a lot of paper by just making it electronic.
Are we done filming?
So that you don't even get your grades banner until you fill them out. It can all be automated, wouldn't it? And then actually get feedback from everybody that was registered for the class who wants the grade.